Morning, everyone. How are we doing? Questions while we wait for everybody to come in? We were looking at double integrals. How's that going? We want to show that the maximum rate of change occurs in the same direction as the gradient. Well, I mean, we proved that in general, right, Yishen? We proved that let's recall the directional derivative, as we saw in the direction of a unit vector u, was the gradient of f dotted with u. And as you know, this is length of gradient, length of u, cosine of the angle between the two. So this is less than or equal to, because of this cosine, cosine is between -1 and 1, so this is less than or equal to this. And in fact, equality is achieved if theta is 0. So when u is in the direction of the gradient, and that proves it. So we don't need to prove it for a particular example. We've proven it in general. You can use the second derivative test. Very nice. Very nice. But that's only going to give you local max and min. There's a second question. Near the point 111, the curve of intersection. We have not discussed that yet. Curves of intersection. We're going to look at those later on, probably by the end of this week or on Monday. Ranji is asking how to find the second derivative of a function. I'm not sure what you're asking here. That question might not really make sense. Well, no. Let's not say that. If you're given a function of two variables, you know how to find the second derivative. So there's no hesitation there. Yishen is asking, can we consider z as a function of x and y, directly differentiate with respect to x and y, and z will become dz dx? Yeah, exactly. Well, are you talking about this example here or Ranji's question? In fact, I think either way you're fine. Find the maximum volume of a rectangular box that can be inscribed in the ellipsoid with sides parallel to the coordinate axes. Tony, did we not discuss this in a email, you and I? No? Am I thinking about somebody else? You've got some well, I mean, look, let's do it in the two variable case. Suppose you have an ellipse and you want to inscribe a box inside some ellipse. So vertex is going to be on the ellipse, right? This point xy, this vertex, satisfies this equation. So this is x, and this is y. So here, this length is 2y, and this width is 2x. So the area is 2x times 2y, or 4xy, subject to this condition. You can use Lagrange multipliers, or you can solve for y, plug it in here, and then you just get a function of one variable. In 3D, it's the same thing. It's exactly the same thing. Find the tangent plane and the normal line to that business. Nishan is asking, sine of x, y, z equals x plus 2y plus 3. You say 3x, but I'm going to assume it's 3z at minus 2, 1, 0. So like you said, yeah, absolutely, you've got options, right? You can find the zdx using implicit differentiation, or and dz dy, and then use the normal minus dz dx minus dz dy and 1, or if you bring this to the other side, then what you have is a level surface. So you can take the gradient of this. And the gradient is normal to the level surface. Both methods give you the same answer, as you would expect. Lara, there are no mistakes on web work, so perhaps there's a slight error in your work, or maybe you're misunderstanding the question. You can send me an email. We can discuss it via email. Last time we ended I was going to remind you of the mean value theorem in Cal 2. Tony, absolutely. Normal line and the gradient can both be used to find the tangent. Well, I'm not sure what you mean by normal line there, but normal way or implicit differentiation, let's say this. Implicit differentiation or the gradient can both be used here to find the tangent plane. Let's recall the mean value theorem in that we saw in 141, which said that if you have a continuous function on a closed and bounded interval, then there exists a point where the area underneath the graph is the same as the area of this rectangle. Right? So the area underneath the graph, which is the integral, is the same as the area of this rectangle, which is height times width. As long as your function f is continuous. That was the mean value theorem in Cal 2. We have an immediate generalization of that, and the geometric interpretation is exactly the same. If you have a continuous function, on a closed and bounded domain, then the volume underneath the function there exists a point x0, y0 where the volume underneath the function, which is the double integral, is equal to this cylinder, if you will, with base d and height f of x naught, y naught. So height times the area of d. So exactly the same idea, an immediate generalization, and this extends to higher dimensions as well. In here, we had defined f of c, which is 1 over b minus a times the integral. We had defined this to be the average value and we can do exactly the same here. This f of x naught, y naught, which is 1 over the area of d, times the integral, is known as the average value. Let's take an example from the book. Find the average value. Average. Let's take a moment and graph this, see what happens. What are we looking at? Because you know you've had time to practice the double integral and you've understood that it's the setup that's important. By the way, I'm sure you've all noticed that the midterm marks were up, right? And I've given you access to the midterm itself, and I've posted solutions on my courses, so have a look at that. What are we looking at here? Y equals 0 is the x-axis. Y equals x squared is this, and x equals 1 is that. So this is the region we're integrating over. Sorry. All right. Well, let's start by finding the area, right? Because the average value, we're going to divide the integral by the area of this region. And you know how to find the area of that region, right? The area is just the integral underneath the function y equals x squared. Which is easily seen to be 1/3. Now, let's take this time to point something out. The area here is, of course, just a single integral. However, let's look at our region again and imagine there was a function hovering above a function which had height 1. Then this would give you a volume, right? The volume of this wedge, if you will, you would integrate 1 over the region. But think about what's happening. You're going to have an area of, well, you're going to have some area on the bottom, and then you're going to multiply by 1 to give it height. So numerically, the answer is going to be the same as the area. It's only going to be the units that are different, right? Instead of centimeters squared, you would have centimeters cubed. So integrating 1 over this region, how would we set that up? Y would vary from 0 to x squared, and then you project onto the x-axis and you get the integral from 0 to 1. Observe what happens here. There is no y, so the integration is trivial. And you get exactly what you had before. Integrating 1 over a domain gives you the area of the domain. In the same way that if you were integrating function which is always 1 over an interval AB, what would that give you? That just gives you B minus A, which is the length of the interval. Even though this is really an area, this area, numerically it's equivalent to the length. And the same thing is happening here, just 1 dimension higher. Quinn is asking, did we choose 1 because you set the height to be 1? Exactly that. And if you integrate 2, you get 2 times the area and so on, absolutely. And Ahmad is asking, is that because the integral of dA is A by definition? Well, that's the idea, right? That's why we use this notation, this dA business, meaning an area component, because the integral of 1 dA is just the area A, absolutely. So that's why this notation makes sense, and that's why it's in use. So let's finish up our average value question. So first of all, a very nice and important observation, right? Well, let's go back to here. The single integral of 1 gives you the length of the interval you're dealing with. The double integral of 1 gives you the area of the integral, of the region. So our average value, which is 1 over the area times the double integral, I forget what we had, I want to say x sine y. Is that it? X sine y, absolutely. Where y varied from 0 to x squared, and x varied from 0 to 1. Well, very nice, Pun. Pun is asking if the triple integral is the volume then. Absolutely. We'll see probably tomorrow that, we're going to define the triple integral after we're done with the double. We're going to define the triple integral, and that corresponds to some hypervolume, right? In the same way that the double integral corresponds to the volume underneath the function, a triple integral corresponds to a 4-dimensional hypervolume. But if you integrate the function 1, it's going to give you the actual volume. Absolutely. So a mod triple integral of dv if x, y, and z all vary. Exactly that. Nima is asking, oh, Nima has figured it out. Very good. Right? I mean, again, the idea, you describe how y varies, and then you project onto the x-axis, getting 0 to 1. If x depended on y here, if the limits depended on y, you would not get a numerical answer. So let's integrate. Integral is trivial here. Antiderivative of sine is negative cos. So you get x times 1 minus cos squared. No, cos of x squared. Is that correct? Work that out. I think that's right. And let's finish that up. 1/2 x squared minus 1/2 sine of x squared between 0 and 1. There it is. What if 1 of x, y, or z were constant? Would the triple integral be needed for the volume? Well, that's the thing, right? I mean, it's not necessarily needed. You don't, right? I mean, compare with what we just did. To evaluate an area now, you have two options, right? You can set it up as a single integral, or you can set it up as a double integral and integrate 1. And this idea is going to extend to higher dimensions. To set up a volume, you could set it up as a double integral, the volume underneath some function, or you could set it up as a triple integral where the integrand would be 1. But enough talk about the triple integral. Let's really finish our work on the double integral first, and let's do one more example. One more example, which is an important one. All right. Let's graph this. In fact, let's graph the equals 1, right? Because here it's an inequality, meaning it's everything bounded by this. It's everything inside. But let's start by graphing this, see what happens. Well, I mean, look, you have experience with the absolute value. You know what to do. If x and y are both positive, then the absolute value of x is just x. And if y is positive, the absolute value of y is just y. So this is x plus y equal to 1, or y is equal to 1 minus x. In the case that x and y are positive. So in this first quadrant, this is the curve. Y is 1 minus x. But now let's be smart. I mean, look, you have options. You could split it up according to when x is negative and y is positive, and when x is negative and y is negative, and when x is positive and y is negative. That's fine, and you'll get the right thing. But let's be even smarter and say, well, notice that this is even in terms of x. If you plug in a negative x value, it's the same, which means there's going to be symmetry about the y-axis. And it's also even for y. If you plug in a negative value of y, it's the same thing. So there's going to be symmetry about the x-axis. And there it is. So our domain D is everything inside. All right. Our domain D has both symmetry about the x-axis, about the y-axis, and the x-axis. And now look at your function. Look at the integrand. Don't look at all of it. Just look at this part. For any point xy in this domain, you have a corresponding point x negative y, right? I mean, it's symmetric about the x-axis. And when you plug in the point xy into this function, you get this height, x squared y cubed, right? So imagine doing a Riemann sum argument. Near this point, you're going to have this height, this positive height, xy cubed. And near this point, you're going to have a height, if you plug in the point x negative y, you get x squared negative y cubed, which is negative x squared y cubed. So you get a negative height there. So you're imagining again a Riemann sum, positive height here, negative height there. They cancel themselves out. This term integrates to 0. Yishen is asking, can we integrate the area in the first quadrant and multiply by 4 to get the answer? No. Because in the first quadrant, this will be positive, and it gives you a positive answer. But in another quadrant, it's negative. And my claim is that since this is odd in y, and your domain is symmetric about the x-axis, this term integrates to 0. And Ranji is pointing out that we're not finding the area. Correct. We're not finding the area. We have this function hovering above, so it's really a volume, if you will. Volume when the function is positive, negative of the volume when the function is negative. But my point is that you can cut down your work a lot by noticing that this function is odd in y. Your function is, your domain is symmetric about the x-axis, so this term integrates to 0. Now, this is even in y, but odd in x. And for any point xy here, you have a corresponding point negative xy. You have symmetry about the y-axis. And Chris has pointed out that the y squared sine x term also disappears, right? Here, you'll have some positive height of y squared sine x, and here sine of negative x is negative sine x. So you'll have a negative height over here. So again, a Riemann sum argument, positive height there, negative height here, cancels out. This integral will cancel out as well. So instead of working with 3 terms, 2 of them cancel out and become 0. So Kuhn is suggesting to cancel 2 conditions have to be met, symmetry and odd integrand. That's exactly it. Absolutely. This will allow you to cancel out. Symmetry of the domain of integration and having an odd integrand in the correct variable. And as Ranji has correctly pointed out, just because the volume is negative in some region doesn't mean that the volume cancels out. Correct. But here it does. Right? In the same way that if your function is negative here and positive there, it doesn't mean that the integral cancels out. Of course, the negative region here is much smaller than the positive region there. So those will not cancel out. But here that doesn't happen. Here they're exactly the right thing. So this cancels out, and now you just have the integral of 2. If you factor out the 2, you get the integral of 1, which is just twice times the area. Right? The integral of 1, we had noticed, was the area. So all you need is the area of this square, which is really 4 of these triangles. Triangle of base 1 and height 1. So the area is 1/2 base times height. So 1/2 times 4. And there it is. The integral is 4. There was nothing for you to do. Yishen is asking, we don't need to integrate these 2 terms in the 3rd quadrant. Well, I'm suggesting that you had symmetry above the y-axis, right? So if you fix any point x, y, you have a corresponding point, negative xy on the other side. If your point was here, if this was your point xy, then on this side, this would be a point negative xy. So, I mean, the 3rd quadrant is, of course, important. We absolutely need symmetry about the y-axis. How do we do the very last step to get 4? Once you've pulled out a 2, you've recognized this as being the area of D, area of the domain. So all we need, right, I mean, it's going to be twice the area. And of course, there's symmetry, right? This region, this area is the same as this area, which is the same as this area, which is the same as this area. So I just need to calculate one of them and multiply by 4. And these are just triangles of height 1 and base 1. So the area is base times height over 2, 1 times 1 over 2. So this is the area of each triangle, and you've got 4 of them. There it is. So 4 times the area of the triangle. Wait, Tony first. I don't understand how the volume from xy can both cancel. No, it's not. The volume xy isn't going to cancel 2 of them. It's only going to cancel 1 of them, right? If this is your xy, if you take a point xy on the right-hand side, of the y-axis, there's a corresponding point, negative xy, on the left-hand side. And those two cancel out. That's what cancels out. So Ranji is asking for, so is for the volume or just the integral? It's the integral. 4 is the integral, which is twice the area, which is also the volume of a function of height 2 hovering above this. Because in Cal 2 we talked about the integral is different from the area. Right, well again, when the function is positive, the integral is the same as the area. And same thing here. When the function is positive, the integral is the same as the volume. Lyra is asking if we can integrate it directly. Of course you can. And please do so to convince yourselves that each of these terms go to 0. So work it out, and there's nothing wrong with that. However, it is time consuming. And this observation is an important one. It's important in this course, and it's a lot more important in the next course you're going to do, advanced calculus, because over and over again you're going to use that argument so as to not integrate a lot of terms. So to find the average value, the area in the denominator is going to be 1/2 times 4. Indeed, absolutely. Yeah, in Math 264, this idea of canceling out odd terms is used over and over and over again for obvious reasons. And you know, we're going to be using that as well in this course from now on. And if you think back to the 141 final exam, there was a question like that on the 141, right? You had an odd function from -10 to 10. You could conclude that the integral was 0 just by noticing that it was an odd function. How are we doing here? Questions? I want us to now consider a new coordinate system, which will be very useful in the double integral. If we're looking at the xy plane, we can completely determine a point by saying how far along you go on the x-axis and how far along you go on the y-axis. And that completely determines a point xy. There are other ways of describing these points. You can say how far you are away from the origin. Let's say r is in radius, and what angle this ray makes with the positive x-axis. And if you're given a value of r and theta, this again will completely determine what point you're talking about. This new coordinate system is known as polar coordinates. And notice that in dealing with this, you're really working with a right angle triangle, where this is x and this is y. Sine of this angle is opposite over hypotenuse. And cosine of that angle is adjacent over hypotenuse. And so we get x is r cos theta and y is r sine theta. These are known as the polar coordinates. Well, the obvious question arises, when is this useful? Why is it useful? Well, we will soon see that complicated functions or curves may have a simple representation in terms of polar coordinates. In particular, consider the circle centered at the origin, x squared plus y squared equals 9. I mean, you know, we've worked with this, and you know that it's a bit difficult to work with. First of all, this isn't even a function by the vertical line test. And so you have to split this up into two pieces, the positive square root and the negative square root. And I mean, you know, it's a bit painful sometimes to work with that. You know, imagine integrating this and so on. It's not easy. In polar coordinates, though, if x is r cos theta and x is r sine theta, if you plug that in, if you transform this into polar coordinates, this is r squared cos squared plus r squared sine squared, and r squared plus, cos squared plus sine squared is 1. So if you factor out an r squared, you get cos squared plus sine squared, which is just 1. In other words, r is plus or minus 3. In other words, this complicated, somewhat complicated function, this complicated circle, this complicated equation to work with in the x and y plane really has equation r equals 3 in polar coordinates, right? Think about it. You are looking at a function which is always 3, right? Because r is the distance from the origin. So you're looking at all collection of points which are 3 from the origin. a very easy description to work with. So Ahmad is asking, we convert the double integral into polar coordinates when we see that the bound is a circle. That's a possibility. You don't, again, you never have to do anything, but we will be doing that, yes. Quinn is suggesting, would we have to convert our result back to Cartesian coordinates if we first convert our integrand to polar coordinates? The answer is no. As opposed to Cal 1, where we would be finding antiderivatives, here we're not interested in that. It's always going to be a definite integral. So we're always looking for numerical answers, never a general antiderivative, so that issue does not come up. And Tony is asking, can we integrate with polar coordinates? We're going to be doing that shortly, absolutely. And that is somewhat of a U substitution. Yishen is asking, R is always positive because it's the distance. Well, that brings up an interesting question, right? If we fix a value of theta, right? So Yishen's question is R always positive? Is the radius always positive? If we fix a value of theta, then this would be the positive R direction. And consequently, it now makes sense to introduce a negative R value and say if this is the positive direction, then this is going to be the negative direction. The opposite. And there it is. And then consequently, as Ahmad is pointing out, some polar coordinates can be equivalent to each other. Absolutely, right? When you're given a point xy, two different points are not equal to each other unless the first coefficients were equal and the second coefficients were equal. This is not the case for polar coordinates, right? In polar coordinates, if you take a point here, and if this is the angle theta, if you were to go another 2 pi, another 360, you're back where you started. So, in fact, every point has infinitely many representations in polar coordinates. And Quinn is asking, why is the 3 positive here? You could have gone, it could have been negative, right? So instead of going a positive direction of 3, you could have gone a negative direction of 3 for all points, and that would have actually given you the same thing. Absolutely. And Cecile is suggesting, can we just use theta such that theta is negative? Absolutely. Let's do a few examples of all of these things, but that's exactly where we're headed with that. The R can be negative or positive. The theta can be negative or positive, right? And if theta is measured from the positive x-axis going counterclockwise, then a negative value is going to be measured clockwise. The opposite of what you were doing. So let's start with a few examples. Page 692, the question is asking us to plot the points whose polar coordinates are given, then find two other pairs of polar coordinates of this point, one with a positive r and one with a negative r. So r theta is given as 2 5 pi over 6. Let's start by plotting this on the xy plane. So we're going to measure an angle of 5 pi over 6. This is almost pi, which is 180 degrees. Right? So we're just stopping short, 30 degrees short of pi. So that's 5 pi over 6. And then you're going to go a distance of 2 along that ray. Right, so there's the point, r equals 2, theta equals 5 pi over 6. Let's describe this point, this same point, in a different way, right? If you keep going, now another 2 pi, you're back here. Right, so if you add another 2 pi, it's going to give you the same point. And as Ahmad is suggesting, if instead you go a direction of negative pi over 6. Oh, actually, he went this whole region, which was 11 pi over 6. So if you're at 11 pi over 6, you're on this ray, and instead of going a positive direction, you're going to go a negative direction. So this is the same as negative 2, 11 pi over 6. Or I was going to suggest negative 2, negative pi over 6. You've got plenty of options. And I mean, this is only 4 possibilities. You have infinitely many others. So Brun is suggesting that polar coordinates are a new system to define coordinates of a point, but still evolves in a Cartesian system. Exactly that. Exactly that. For now. In the sense that we're having it live in the xy plane, absolutely, but you could, if you wanted to, not that you usually do, but you could have it live in the r theta plane. And it's usually not an important thing to do, but sometimes it is. Ahmad is asking, can we generalize these possibilities in a closed form? How do you mean? You mean instead of polar coordinates, some general idea? While Ahmad is answering that, let's take another example. Same question. Different r and theta value. Again, let's graph that. And then we are looking for, so theta is negative 2 pi over 3. So instead of going a direction of 2 pi over 3 in the positive, we're going to go 2 pi over 3 in the negative. And then a direction of 1, a distance of 1 from the origin. Absolutely, Ahmad, yes, thank you. You can in fact add any multiple of 2 pi to any of these angles theta, and in general this would be correct, absolutely. So Sid is asking, do the properties when used for complex numbers apply here, like squaring or adding? There's a very did you mean complex numbers, or did you mean vectors? Because it's interesting that there's a nice relationship between polar coordinates and complex numbers, but yeah, I think you did mean viewed as vectors. I think so, right? Meaning that can you add two of these vectors? We're not going to do that. We're not going to do that because these are these are not going to be vectors, are not going to add in a good, significant way. So short answer, no. Right, as opposed to a point xy, which can be confused with a vector xy emanating from the origin to that point. We're not going to do that here because it's completely different, right? This measures the angle, whereas this measures the distance. So let's not do that. But there it is. And we want to answer the same question. Is this equal to something else? I mean, if you measure the positive, what would be the measure of the positive angle? Instead of negative 2 pi over 3, I believe this is going to be 4 pi over 3, right? Because when you add these two angles, you get 6 pi over 3, which is 2 pi. So you're back to here. So this point is the same as that point. And if what? If this is going to be pi over 3. So this should be pi over 3. So this should be 2 pi. No, what have I done? This is pi over 2. This has to be pi over 3. So this should be pi over 6. That does not look right. Probably my picture's off. No. What have I done? Jeez. What is this angle? This angle was pi over 2. And the whole thing is 2 pi over 3. So this has to be pi over 6. Pi over 2 plus pi over 6 is what? This is 3. This is 4 pi over 6, which is 2 pi over 3. So that's what we have. So this angle is pi over 6. So this angle should be pi over 6. So this angle has to be pi over 3. Here we go. Right, because pi over 3 plus pi over 6 gives you pi over 2. So this is going to be the same as if you go an angle of pi over 3, and instead of going 1 in the positive direction, you're going to go 1 in the negative direction. Here we go. So minus 1 pi over 3, thank you, Bren. Exactly what we finally came up with. All right, very nice. Consider the following question, which is asking us to plot the point with the given polar coordinates and find the Cartesian coordinates of that same point. So r and theta well, that's very similar to what we just did. Why don't we skip that? Take a moment, graph that. And then we're going to ask, what is the Cartesian coordinates? What are the Cartesian coordinates, x and y? You can, right, Thomas? Thomas is suggesting, can we just subtract or add pi to the initial angle and take the opposite? There are several things you can do, but here we're not asking the same question as before, right? We're not asking for different values which give you the same point. Rather, they're asking us to graph this. So if you go an angle 3 pi over 4 counterclockwise from the positive x-axis, you're right here. And then you're going to go a distance of -2. So instead of going 2 in that direction, you're going to go 2 in this direction. And here you are. This is the point we're looking at. What we want is the xy coordinates of that point. But you know, in polar coordinates, x is r cos theta, y is r sine theta. So in this case, if r is -2 and theta is 3 pi over 4, Ahmad wants to know about the midterm average. Did I not release it on my courses? I thought I released it. In any case, right. Thank you, Jennifer. I did release it on my courses. I believe it's 81 point something. Very high. Yeah. Yeah, something around 80, 81. When r is -2 and cosine and theta is 3 pi over 4, cosine of 3 pi over 4 is -1 over root 2. So you get 2 over root 2 here. And sine of 3 pi over 4 is 1 over root 2. So you get -2 over root 2 here. And there it is. Or if you prefer, root 2, negative root 2 is the point. Which Makes a lot of sense, right? We were expecting a positive x, but a negative y. Will what be released, Avery? I did release the midterm exam itself, and I don't know if I can release any marks on crowd mark as far as average is concerned, but all the information is on my courses. When it's asking, is it harder to convert from Cartesian to polar? We'll do that in a moment. It's actually slightly more work, but not that much. Let's do maybe one more. And then we'll do the opposite. Right, so it's very easy to convert from polar to Cartesian. What about the other? Well, so first of all, let's graph this. An angle of negative pi over 3 is right here. And if this is the positive direction, then the negative direction is going to be right here. Without doing any work, what are we expecting? We're expecting a negative x and a positive y. Right, so x is r cos, y is r sine. These are the x, y. These are the polar coordinates. This point here, x, y. Cosine of negative pi over 3 is the same as cosine of pi over 3, which is 1/2. So we get a negative 3 over 2. Sine of negative pi over 3, you know that sine is odd, so that is negative of sine pi over 3. And sine of pi over 3 is root 3 over 2. So negative root 3 over 2 times negative 3 is going to be positive 9 over root 2. No. It was a root 3 over 2, so 3 root 3 over 2. There it is. Can the angle be expressed in degrees? No, we don't want to do that. Let's not do that. Let's not talk about degrees. As you know, radian is the way to go. Let's do the opposite. Cartesian coordinates are given. Find the polar coordinates. So x, y are given. We want to find the corresponding r and theta. First of all, you know what's happening here. Root 3 in the direction of x, negative 1 in the direction of y. This is the point. This is the point root 3 minus 1. If we want to convert to r and theta, all we need to do is figure out how far it is from the origin, and then what angle this ray makes with the positive x-axis. Or, of course, it could have been this angle. Either way, it doesn't matter. Again, you have many options, but what? Let's talk about the distance from the origin. of course, you recognize that this is just the length of the vector. So Pythagorean theorem or whatever, right? I mean, it's just the length of the vector. So R is the length of this vector. Or, if you have a point xy in general, the length is the square root of x squared plus y squared, which we saw arising naturally in the circle example, right? We saw that r squared was x squared plus y squared. So it's just the length, r is just the length of the vector. There it is. R can be dependent on theta. Absolutely, right? Because of course you could have taken this as the angle, and then it would have been a negative r. So again, there are different approaches, but if you go with that, we're good to go. That's what r is. So here, this is the square root of 3 plus 1. So it could have been, it's plus or minus 2, right? Depending on which ray you take, but let's go with the positive. So r is 2. And now look at your polar coordinates here. How, right? I mean, observe that if you divide y is r sine, x is r cos, the r's cancel out nicely, and this is just tangent of theta. So y over x is tangent of theta, and consequently theta is the arctan of y over x. And that gives you the theta in general. So here r is 2 and theta is arctan. So in this case, arctan of y over x. There it is. You might not recognize it, but I claim that this is negative pi over 6. Sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. So you get a 1 over root 3, and then with the negative, it all works out. Can you just use x to find theta? You can, since you already know what r is going to be. Absolutely. You can do that as well. There are many options, but what we're saying, r theta, in this case, 2 and negative pi over 6 work fine. Let's do one more. And then we'll get to the real business. Right, this is xy here. So x is minus 6, y is 0. There it is. Could you say 2 and 11 pi over 6? Absolutely. Right? You could also say 2 and 11 pi over 6. And you could also say 5 pi over 6 and negative 2. And so on and so on. You could add 2 pi to any of these. Well, if you add 2 pi to this, you get that. So that's a nice observation. But there it is. All right, one more, one easy one. You know what's going on, right? What is the angle here? 180 degrees or pi. And once you've got 180 degrees, what is the distance you want to go? Distance of 6. In the exam, we'll be clarifying the problem whether a point is in polar or Cartesian. Yeah. It should be right. I mean, I'll either say r theta or xy. But short answer is those questions will not come up because it's too easy. It's only the beginning. You're not going to get anything this trivial on the exam. Where are we going with this? Well, we wish to graph. Mud is asking, would the integral of a function in normal coordinate system with respect to x and y be the same as a function in polar coordinate integrated with respect to r and theta? It's a valid question. Our ultimate goal here is going to be to make a change of variables from the xy coordinate system to the r theta coordinate system. So a change of variables similar to a u substitution, if you will. I don't want to give it away. Some of you may already know the answer. But short answer, yeah. Think of, here's my suggestion to you. Think back to Cal 2. If you made a u substitution, or if you made a trig substitution, you had to account for what dx was. The same is going to happen here. Here you're going to maybe transform x as a function of u and v, y as another function of u and v. And then the question is going to come up, what is dy dx in terms of du dv? But before we consider that, let's talk about graphing. There's an obvious way to graph. If you're given r as a function of theta, you can plug in your function theta into your polar coordinates, and for every value of theta, you get a point xy which lives on your graph. And then you could plot all these and sketch your curve. Very time consuming, very long, boring, and really not an efficient way to make use of how we defined polar coordinates. Instead of doing that, we're going to go back to the definition of polar coordinates. And how did we define polar coordinates? Well, we said theta was the angle measured from the positive x-axis going counterclockwise. And r was the distance away from the origin on each of these angles. And that's how we're going to graph. Let's take an example. Suppose you want to graph the function r equals sine theta. Here I've plotted a few angles. This is theta equal to 0. Theta equals pi over 6, pi over 4, pi over 3, pi over 2. 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And then you could keep on going. 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, and so on and so on. When theta is 0, what is sine of 0? You know what sine of 0 is. So sine of 0 is 0. So when theta is 0, you go a distance of 0 away from the origin. In other words, you're at the origin. Sine of pi over 6 is 1/2. So on this angle, on this ray, go a distance of 1/2 away from the origin. Sine of pi over 4 is 2 over root 2. So go a distance of 2 over root 2 on this ray. Sine of pi over 3 is root 3 over 2. Sine of pi over 2 is 1. Well, before we continue, let's remind ourselves of what the r equals sine theta graph looks like in the theta r plane, right? Or y equals sine x in the xy plane. You know what it looks like. And we're going to use this to help us graph, right? It starts at 0, and then it's increasing all the way to 1 at pi over 2. Starts at 0, and it's increasing all the way to 1 at pi over 2. Then what? Then you decrease back down to 0. And you see the symmetry? It's the same thing. Decreases back down to 0 at pi. Decreases back down to 0 at pi in the same way that it increased before. What about after? What happens after pi? After pi, sine is now negative. So instead of graphing it in this positive direction, you're going to graph it in the opposite direction. Again, with the same symmetry, right? This piece is the same as that piece. So it's going to overlap exactly the same, right? Sine of 7 pi over 6 is negative 1/2. So instead of going a direction of 1/2 in this, instead of going a distance of 1/2 in this direction, you're going to go a distance of 1/2 in the opposite direction. Sine of 5 pi over 2 is negative 1 over root 2. So instead of going a distance of 1 over root 2 in this direction, you go a distance of 1 over root 2 in the opposite direction, and so on and so on. It overlaps exactly upon itself until you get to 2 pi, and then what happens at 2 pi? You start over again. There it is. This is the graph of r equals sine theta. And all you needed to graph this was theta between 0 and pi. Anything outside of that just overlaps on itself. How are we doing? Well, I mean, let me ask you this. It looks like a circle. Is it? Is it really a circle? Or does it just look like that because our graphing skills weren't all that good? Maybe it's elliptical shape. Who knows? Let's figure it out. Is this really a circle? This is what we're graphing. Right? This is what we're graphing. Let's translate this into Cartesian coordinates. Let's translate this into x and y. Multiply both sides by r. This becomes r squared is r sine. R sine, you've seen this before. R sine is y. What about r squared? We saw that before as well. R is the square root of x squared plus y squared, right? It's the length of the vector. Or r squared is x squared plus y squared. We also saw that when we were looking at the circle. So we have in Cartesian coordinates in the xy plane, r equals sine theta is really x squared plus y squared is equal to y. Still questionable. I'm still not sure what that looks like. Let's bring the y to the other side. Still doesn't really do it, but let's complete the square. Let's add 1/4 to each side. If you add 1/4 to each side, now you see that this is really y minus 1/2 all squared. And now you see that it's a circle of radius 1/2 centered at 0, 1/2. So 0, 1/2. A circle centered at 0, 1/2 of radius 1/2. Now we're guaranteed that it's a circle. But you see the beauty of the polar coordinates now, right? You had this complicated equation in the xy plane, very simple description in polar coordinates. Let's take another example. R equals cosine. You know what's happening, right? First, let's draw it in the r theta plane. No. Theta r plane, right? You know what cosine looks like. It starts at 1. And so on and so on. We're going to translate that to the x theta plane. At 0, theta cosine is 1. So we're going to start a distance of 1 away from the origin. And as you move to pi over 2, what is happening to theta? What is happening to r? R is getting smaller and smaller all the way to 0. So the distance as you move to pi over 2, the distance from the origin is getting smaller and smaller all the way to 0. And then what? After pi over 2, cosine is negative. So instead of drawing it in the positive direction here, you're going to graph it in the opposite direction. And what is happening? You're going from 0 down to -1 at pi. So you're going to start at 0, and the distance is going to increase all the way to -1 at pi, which is going to overlap with this. Right? So at pi, you're at -1. And then what happens? From pi to 3 pi over 2, right? So in this third quadrant here, for angles in here, cosine is still negative. So you're not going to graph them here, but rather in the opposite direction, again, completely overlapping with your circle on this side, right? Here at 7 pi over 6, cosine of 7 pi over 6 is going to be -1/2. No, -√3 over 2. So instead of graphing it in this direction, √3 over 2, you're going to graph it in the opposite direction. a distance of root 3 over 2 is going to overlap exactly on this again. Is that the same if we just look at the positive cosine term because it's repeating, but we need to analyze more? I think we need to analyze a bit more. Just because it's repeating doesn't mean you have to be careful. You have to be careful, and we're going to do a few more examples which illustrate the issues you want to be careful with. But there it is. Again, right? So first of all, what am I suggesting? We have graphed this circle from 0 to pi. And then if you graph it from pi to 2 pi, it repeats over itself again. And then at 2 pi, you're back where you started. And then you know cosine is just periodic of period 2 pi. So really, you have graphed the whole thing in 0 to pi, and it just repeats itself again. I've referred to it as a circle, but again, it's not immediately clear that it is. Is this a circle? And if you multiply by r again, you get r squared is r cos, which is really x squared plus y squared is x. So in very much the same way, bring the x over, complete the square, and you see that you get a circle of radius 1/2 centered at 1/2, 0 right here. So again, this rather complicated curve has this nice, simple polar coordinate description. Let's look at a few more curves. And I've got the r equals cosine curve right here, so let's make use of that. It's very good. And what is happening? When theta is 0, cosine is 1. So when theta is 0, you're starting at r equal to 0. In other words, you're not moving away from the origin, you're at the origin. What is happening to cosine? Cosine is going to decrease all the way to 0 at pi over 2. So this is going to increase from 0 all the way to 1 at pi over 2. Pi over 2 is right here, 90 degrees, right? So you're increasing all the way to 1 at pi over 2. Then what? Cosine is still decreasing all the way to -1 at pi. So this is going to continue to increase all the way to 2 at pi. So this is getting larger and larger. And then what happens? Well, then the opposite happens. You start to increase all the way to 0 and all the way to 1. Well, all the way to 0 at 3 pi over 2. So the distance is getting shorter, and then your cosine is still increasing. So 1 minus cos is decreasing all the way to 0 at pi, at 2 pi. And you get this nice heart shape known as a cardioid. Imagine having to describe this in x and y. But in polar coordinates, trivial. Let's do the same with that. I had to remove that. It's nice to have. Let's graph this in the xy plane. What is happening? You're starting, when theta is 0, you're starting at, cosine of 0 is 1, you're starting at a distance of 3 away from the origin. What is happening to cosine? Cosine is decreasing, right? All the way to 0 at pi over 2. So this is going to decrease all the way to 1 at pi over 2. And this keeps decreasing. Notice that this is going to become -1 at some value, right? When cosine is -1/2, when cosine is -1/2, so namely at pi over 2 plus a pi over 6, so 2 pi over 3, at 2 pi over 3, cosine is -1/2, so this whole thing is 0. So at 2 pi over 3, you are now at 0. And what happens after? Well, cosine becomes even more negative. So this is going to be less than -1/2. So the whole thing is going to be less than -1 plus 1. The whole thing is going to be negative. So instead of graphing it in the positive direction now, you'll be graphing it in the negative direction. So this goes from 0 all the way to -1. So this is going to increase in a negative direction all the way to 1. And then, well, then you know how cosine behaves. The opposite. So now it's going to increase all the way to -1/2. So you're going to increase all the way back to 0. And then keep increasing all the way back to cosine being 0, so all the way to 1, and then all the way to 3. So Cecilia is asking, since cosine and sine are periodic of period 2 pi, can we generally say that the graphs repeat for every 2 pi? Absolutely. Absolutely. If you're graphing something that only involves sines or cosines, then for sure you're going to have this periodicity. If, however, it's a graph not involving sine or cos, then you want to be careful, right? And the period might be shorter than 2 pi, as we saw in the r equals sine theta or r equals cos theta, where the period was actually pi. But there's our graph. Very nice, right? I mean, again, imagine having to describe this in x and y. You have some graph looping on itself. I mean, you never see that. It's a nice exercise to rewrite this in terms of x and y by doing the same trick we did before, and you get this complicated equation, and this is the graph of that equation. So very complicated in terms of x and y, relatively straightforward in r and theta. And that's the beauty of the polar coordinates. Let's do a few more examples. Yishen is asking, can we graph tangent? You can. You can. I'm going to let you work that out. You understand, though, tangent being sine over cos, when the denominator gets, when theta gets close to pi over 2, the denominator goes to 0, so your whole function blows up. So r, which is the distance from the origin, gets larger and larger. So that's a nice thing to graph. Let's not do that, though. Let's work our way up to more complicated functions by looking at sine of 2 theta. Now again, you know what sine of 2 theta looks like in the r theta plane. Right, in the r theta plane, it's the same as sine theta, except it's twice as fast, right? The period is twice as fast. So you get all of that in 2 pi. So this was pi over 2, that was pi over 4, and so on and so on. Let's use this to graph that. Sine starts at 0, so you start a distance of 0 away from the origin. And what is happening? Sine is increasing to 1 at pi over 4, and then back down to 0 at pi over 2. So increasing to 1 at pi over 4, and then back down to 0 at pi. Everybody with us? Back down to 0 at pi over 2. Right? At 90 degrees, you're back down to 0. Then what's going to happen here between pi over 2 and pi? Well, between pi over 2 and pi, sine is negative. So instead of graphing it in this positive direction, you're going to graph it in the opposite direction. And what is happening? You go from 0 to -1 back to 0. So 0 to -1, so a distance of 1 in the opposite direction, back down to 0. So that's what happened between pi over 2 and pi. And now between pi and 3 pi over 2, pi and 3 pi over 2, this is positive. So in this quadrant, it's positive, and so the graph will be here. And what happens? Start at 0, go all the way to 1, and then back down to 0. And finally, in this quadrant, your function is negative, and you graph it from 0 down to -1. So from 0 down to -1, but in the opposite direction. And back down to 0. There it is. Right, so what happened? Let's go over that again. 0 to 1, back down to 0, and then here, and then there, and then there. This 4-petaled rose, if you will. 4-petaled flower. Again, this would have a rather complicated equation in the xy plane. In polar coordinates, r equals sine 2 theta. Easy to describe, easy to graph. Let's do one more. And then we'll move on. All right. Quinn, perhaps there was a question or just a statement, petals? Yeah. Let's look at this. Again, you know the graph in r theta. Right? It's the same as the cosine graph, but again, twice as fast. So 2 pi, pi over 2, pi over 4. There it is. Let's graph it in the xy plane. What is happening? You're starting when theta is 0, cosine is 1, so you're starting a distance of 1 away from the, I had a question here. If we have sine of 8 theta, do we have more petals? Or does it take a completely different shape? Is there some kind of pattern? There is a pattern. There absolutely is. We'll do a few more and we'll try to generalize what is happening. Not something you should necessarily remember, but something you can take a moment to graph and convince yourself of. Let's look at cosine 2 theta here. You're starting at 1. You're going all the way to 0 at pi over 4. Right, so here you're at pi over 4. And from pi over 4 to pi over 2, you're going all the way to -1. Right, so instead of graphing it in this region, you're going to graph it over here, going from 0 to 1. And then from -1 back to 0, that was in this region. And then in here, you're going from 0 all the way to 1. And then 1 back down to 0. Now you're right here. And then in this, where are we? In this region, you're now in the negative. Finishing up as so. So sine of 2 theta and cos of 2 theta each have 4 petals here. Very nice. Let's look at sine of 3 theta. Just to see what happens. So this is the same as sine of theta, but again, 3 times as fast. 1, 2, 3. Good enough, right? This is 2 pi. So 2 pi over 3. 4 pi over 3. 6 pi over 3. And this is pi over 3. Well, we are quickly running out of time, so this is the last one we'll do. I'll invite you to look at cosine of 3 pi and sine of 4 pi and cosine of 4 pi and so on until you see the pattern developing, but there is a pattern. Again, not necessarily a pattern I want you to memorize. Instead, I want you to be able to come up with these graphs very quickly. That's what you need to do. That's where you need to be. All right, let's look at this. What is happening? Sine is going from 0, so this is going to be half of that, it's going to be pi over 6. Sine is going from 0 to 1 at pi over 6. So 0 to 1, and then back down to 0. At pi over 3. And then between pi over 3 and 2 pi over 3, right? So pi over 3 is here, 2 pi over 3 is here. In this region, sine is negative. So instead of graphing it here, I'm going to graph it over here, and we're going to have this thing right here, right? It's going from 0 to negative 1. So instead of 1 in the positive direction, I'm going 1 in the negative direction, and then back down to 0. And then between 2 pi over 3 and 3 pi over 3, which is pi, so in here, that is positive. So it goes from 0 to 1, back down to 0. Now you're at pi. So in this region, sine of 3 theta is negative. So instead of graphing it here, I'm going to graph it in the other side. And you see what's going to happen, right? It's going to overlap itself. So you might have been tempted to think sine of 3 theta is going to have 6 petals. It does not. It only has 3. As opposed to sine of 2 theta, which had 4 petals. And so on and so on. I'll let you finish that up, but I think you saw that right here we began to overlap. And then in this region, which corresponds to this part right here, sine of 3 theta is going to be positive, so it's going to be mapped in this region. And finally, in this region, sine is negative, so you're going to map it here. There's going to be exact overlap. There it is. Before we do anything else, let's take a moment to do a nice exercise. The question is asking us to identify the curve by rewriting this in Cartesian coordinates, in x and y. You know secant is 1 over cosine. So that's really r equals 4 over cos. If you bring the cos to the other side, and r cos is really x, right? Because the polar coordinates, x is r cos. So r equals 4 secant is really the same as x equals 4. This is a vertical line. Right? Think about what's happening. When theta is 0, r is a distance of 4 from the origin. And as theta increases, gets larger and larger, closer and closer to pi over 2, the distance from the origin is getting larger and larger. Same on the other side. So here we have the opposite effect, right? Very simple in x and y, rather complicated in r and theta. So sometimes it's easier to convert to one than the other. Let's graph this in the x and y plane. Notice that no r is given here. So theta is pi over 3 regardless of what r is. Theta is pi over 3 for all values of r. Theta is pi over 3 for any value of r. If r is 0, if r is 1, 2, 3, 4, right? So you get this collection of points all along this ray, -1, -2, -3, and so on. You have this straight line. So this is the equation of a straight line going through the origin. Well, right, I mean, you can take sine, or you can take cosine, or in fact, we saw that theta was arctan of y over x. So if you want to convert, you have arctan of y over x is pi over 3. So you could take tangent of both sides. Y over x is tangent pi over 3. Sine of pi over 3 is root 3 over 2. Cosine is 1/2. So you get root 3 here. So y is root 3x. A straight line through the origin. There it is. How are you doing? Questions here? Well, I know what you're thinking. What is the area of one of these petals? Right? Or in general, what is the area of underneath a polar curve, if you will? So suppose you've got some function, r equals a function of theta. Let's do a Riemann sum argument to approximate the area of a polar curve. What are we going to do? We're going to approximate the area using these wedges. These wedges of small change in delta, small change in theta, so let's call it delta theta. This can be viewed as a fraction of a circle. What fraction of the circle? Well, whatever this angle is over 2 pi, right? Think of it as a slice of pie here. What proportion of the whole pie is it? Well, it's that angle divided by the whole thing. So the area of this region is going to be this proportion of the whole area of the pie, where r is your function. And you know, you do this for one thin slice, and then you redo it for another slice and another slice. And you add all of these up to get a Riemann sum. And the area is going to be approximately this. The pi's cancel out. 1/2 f squared delta theta. And you recognize this as a Riemann sum. As the delta theta gets smaller and smaller, you get a better approximation. And this converges to, the sum becomes an integral, 1/2 f squared d theta. This is the area of your, well, the area underneath. And I use underneath in quotations here because you understand how it's measured, right? It's measured from the origin going out. So it's not really underneath per se. It really depends on the function. Let's illustrate with a few examples. We are asked to sketch the curve and to find the area it encloses. All right, let's graph this. Maybe we can simplify it to that. Right, it's really just twice 1 plus cos theta. So if we know what 1 plus cos theta looks like, we can just multiply by 2. It's twice the length from the origin. And again, you know what the graph of cos looks like. So let's make use of that in graphing our function. This is going to start at 2 times 2, so it's going to start at 4. And cosine decreases all the way to 0 at pi over 2. So this goes down to 0 at pi over 2. So the whole thing goes down to 2 at pi over 2. And then it keeps decreasing down to 0 to -1 at pi. So this whole thing goes to 0 at pi. And then the opposite happens, right? It now starts to increase all the way to 0. And then all the way there you go. So the question we wish to answer is, what is the area enclosed by this curve? So you see what's going to happen, right? Well, first of all, there's obvious symmetry. Maybe we can make use of that. It's nice to do that, the area is going to be twice this top part. So let's describe this top part. How do we describe it? Theta goes from 0 to pi. So 0 to pi, 1/2 your function squared d theta. There it is. 1/2 and the 2 cancel out. 2 squared is 4. It's 1 plus 2 cos plus cos squared. You know how to integrate all of these things. The cos squared could we integrate it with dr also? No. No, let's not do that. Let's not do that. Theoretically, you could. Theoretically, you could. Nobody does it. Nobody does that. Nobody does that because why doesn't anybody do that? It's too complicated. It's too complicated. Here you would have to solve for theta in terms of r, and you'd get an inverse cosine, and then it would just be a big mess. Theoretically, you could, but in practice, nobody does it. Cosine squared, you're going to use the half angle identity. You know what's going on here. This is 1/2 times 1 plus cosine 2 theta. So this is 3/2 plus 2 cos theta plus 1/2 cos 2 theta. So 3/2 theta, 2 sine, and 1/4 sine 2 theta between 0 and pi. When you plug in pi into these, you get 0. When you plug in 0, you get 0. So the whole thing is 6 pi. There it is. Let's do one more, and then we'll end with that. I think we had, Yushen is asking, when the angle is pi/2 to pi, why is the graph done in the 4th quadrant? So pi/2 to pi. Remember though, we were graphing r equals 2 times 1 plus cos theta. So even though cosine is negative in this region, so I think Yushen has got it. Yeah, very good. Oliver is asking if I will release the exams on CrowdMark with the corrections. The exams have been released. Yeah, the exams have been released. It will probably be not to your satisfaction, because there are very few remarks probably written on the exam, but you'll be able to see how many points you lost. Probably not why you lost them, but maybe you can. I mean, the corrections have been posted on my courses, so you'll at least be able to compare and determine where you lost your marks. Let's look at this quickly. I think we had already graphed this function earlier today, right? We saw that sine, if I remember correctly, had 3 petals like this. Well, it doesn't look good, but you know what it's supposed to be, right? Where one petal was actually graphed going from 0 to pi over 3. Right? This first petal was graphed going from 0 to pi over 3, and we had convinced ourselves that there were only 3 petals. So we can find the area of one petal and multiply by 3. Right? There's obvious symmetry, even though my graph doesn't suggest there is. The area is going to be 3 times the integral from 0 to pi over 3 of 1/2 your function squared so that's going to be 6, the integral from 0 to pi over 3 sine squared. And you know how to integrate that. Half angle identity. 2 sine 3 theta is just overlapping the graph of sine 3 theta. Well, I mean, it's twice as long, right? That's the only difference. Each petal is twice as big, if you will. Probably a bad choice of words here, but you understand what I mean. Right? The distance from the origin at every point is twice as long. Let's say that. And theta minus 1 over 6 sine 6 theta from 0 to pi over 3. This is 0, and you get just pi. There it is. How are we doing here? Questions? Practice this polar coordinate business. We're going to finish that up tomorrow and then discuss how this applies to the double integral itself, right? Because now we're just in the realm of Cal 2. This is just a single integral. But tomorrow we're going to ask the question, what about the double? Where does that fit in? Where are we going with that? Thank you all for coming. I'll see you tomorrow. Questions in the meantime? Anyone? No? We're good? Can you calculate an area when it's not enclosed? Well, I mean, you're going to have to at least, the question should artificially enclose it in the following sense. Suppose that right? I mean, if you think back to Cal 1, suppose you had this function y equals x squared. This would go on forever, and then they might artificially enclose it at between 0 and 1, as we did in one of our first questions today. And then the analogous thing might happen in polar coordinates if you have a function which continues on forever. The question might ask you to enclose it between pi over 6 and pi over 3. So pi over 6 and pi over 3. So they might ask for just this region here. That's a possibility. Quinn is asking, can't we take the limit like we used to with improper integrals? So are you at, well, yes. Short answer, yes. But it might be a, yeah, so, well, yes. Let's say yes. The analogous thing could come up, absolutely. In most examples, though, they actually restrict their attention to finite integrals. But you're correct that the notion of improper integrals could extend to polar coordinates. Very nice. All right. Questions, anybody? No, we're good? I will see you tomorrow then. If you've got questions, you can email me. Practice these polar coordinates and we'll pick this up again tomorrow. Thank you all for coming. I will see you then.